All right, so we're looking at 6.4, which is elliptical orbits. So Kepler's first law says that all planets will orbit some sort of central mass in an elliptical fashion, an elliptical orbit. So all planets orbit the sun in elliptical orbits. That's our first law. Now, where the sun is located is at one of the focal points of the ellipse. So the sun is at a focal point. It's at the focus. So sun, there we go. Sun is at the focus. Kepler's second law says that if you sweep from where the sun is to where your planet is, and you record a certain amount of time, and then you draw another line from your planet to where the sun is, that this distance covered, it sweeps out equal areas, looking at this whole chunk here, equal areas in equal amounts of time. So if you look at a different location, so we decide to take 1 day or 1 year, 1 month, whatever that time period is, if you take the area here, that is going to be exactly the same as the area here. That all of these guys have equal areas, assuming that it's the same amount of time, the same change in time at each of these locations. So you might notice over here it has gone through a greater area in that same amount of time, which means that you have a much greater speed at this location than you do over here. So when it's really close to that location, really close to that sun, that it's going to have a much quicker speed. So for the second law here, we're going to say that if you draw a line between the planet and the sun, that it sweeps out. And sweeps just means that if you take this line as you move this way, that's the area that we're looking at. It sweeps out equal areas in equal times. The next thing that we have is talking about potential energy. We're going to talk more about potential energy with this ellipse in a second. But looking at potential energy, our original equation for potential energy is this. UG is equal to mgh, or you can also say mg delta y or mgy. But it's the mass times the gravitational field strength times the height, or the change in that y direction. This is a great equation, and it's not necessarily wrong, but there's a couple of assumptions that you make. Firstly, this UG is really the change in potential energy. It's really the change in that potential energy. It's not that it has X amount, it's that from its original position to its new position, it has changed. This delta Y or H, however you want to say it, is really, again, the change in your height. It's the change, how far up you're going. Now, all of this is only true when G is constant. So if you are in a constant gravitational field, so the question is, under what circumstances can we use this equation? Well, it's really when G is constant. Or another way of looking at this is near the surface. Of a planet or sun or whatever object we have in our system. If you are really close to the ground, so here's the ground, we have this force of gravity that's pulling down, and it's equal all the way across. Now, if you look at the big picture, so here's our Earth. This time, if you draw these fields in, and this is just the direction of this gravitational force, notice at this location, these arrows are really closely packed together, but over here, it's much more spread out, which means G is stronger at the bottom, so you have a greater G value than up here. So it is not constant. G is not constant if you look in the big picture. So the question is, what gives the gravitational potential energy of any two objects in the universe? So if you're looking, again, this is big picture. If you're looking big picture here, the equation actually deals with work. If you look at the equation for the universal force of gravity, so typically you do F with big G here, it uses the universal gravitational constant, which is 6.67 times 10 to the negative 11th, times m1, m2, those are the two masses of your object, divided by the radius, or the distance between them, squared. Now, if you think about the work done, work is equal to the force times the distance. So if you take some object and you raise that object away from Earth, you are going to essentially give it a greater change in potential. That's what you're doing. You are increasing that change in potential. And so if we're looking at that, if we want to know the work done to get it to that point, the displacement is this way, but the force, so this is our displacement, the force is this way. So these guys are actually working in different directions. So since they are working in opposite directions, it is actually a negative amount of work. So this is where we get the negative sign. Now it is the force that we had over here times the distance away. Well, the distance away is an r. So what happens is that radius squared kind of gets canceled out there. So it becomes a negative G m1 m2 over r. This is our new equation for the gravitational potential energy of any two objects. So just to kind of write our variables down here, we know G is going to be that 6.67 times 10 to the negative 11th. Units would be Newton meters squared per kilometer squared. M1 and M2 are going to be masses of our objects. Obviously the units here are kilograms. And the last one is R, and R is going to be the distance between the two. Now it is between the center of masses. So you have to look at what your object is, the center of its mass to the center of your planet. This is what we're looking at. That's our radius. Again, we're looking from the center to our object. That's our new equation. Looking at the next part, it talks about setting the 0 point or the origin point for potential energy. You can set it wherever you would like it. You can put it wherever you want. That's why whenever we talked about just the regular MGH, you could make the ground 0, but you could also make the highest point 0, and then you'd go negative if you wanted to. You could also make like the middle or the lowest point 0. You can put it wherever you want. But when we use this new equation, the universal equation for gravitational potential energy, that's what GPE is, gravitational potential energy. When we use the universal, 0 point has to be in a very specific location. So if you think about it like this, 0 is your perspective. Now, if you are infinitely far away from an object, you would have no potential energy from that object. And then, so that would kind of be over here. That would be your infinite. That would be some radius away. This is going to be your potential energy, the amount of potential energy. Now, we said that it's negative, so we're going down below the axis here. And as we go up, this line is going to get closer and closer and closer in this r squared pattern, oops, or this 1 over r pattern so that it fits our equation. There we go. Where this point right here would be the radius of the Earth. Now, there's a couple of things we need to make note of here. Firstly, the zero line, so zero energy, is at a radius that is infinitely far away. This equation is always true. It's universal, so you can use it instead of MGH. You can just use this equation. Obviously, it's a lot easier to use MGH if you're on Earth, but this equation will always be true. The next thing is this equation, if you're looking at each individual gravitational force, is negative. It is less than 0. And one more thing to note is R is not squared like it is in the force. A lot of people will mess up with that just because they're not paying attention to the equation. It is not squared like it is in FG. Now, the reason this kind of makes sense is if you pick 2 points on here, let's say this is your final destination and this is your initial. There we go. Then we should see this change. If you're getting further away, we should see a positive change in gravitation and your universal gravitational potential energy. So if we take these values, let's say that here this is like -10, and we're going to say this is at -20. If you do final minus initial, that's going to be -10 minus a -20, which ends up getting you a positive 10 joules of energy. So as you go further and further away, you are storing energy in that gravitational field. That is all true. You still have a positive amount of energy. It's just if you look at it individually, you have a negative amount. All right, we'll do the rest in just a bit.